Welcome to this lesson on BJT models. BJT stands for bipolar junction transistor. In this lesson, we'll look at the mid-frequency mathematical models used to analyze bipolar junction transistor amplifiers. By the end of this lesson, you will be able to do 6 things. First, explain how amplifiers are classified. Second, describe the need for mathematical models in amplifier circuit analysis. Third, identify the various mid-frequency BJT models. Fourth, describe the h-parameter model. Fifth, describe the hybrid pi model. And sixth, describe the RE model. Let's begin by looking at how amplifiers are classified. Amplifiers can be classified in 6 different ways: by transistor configuration, by conduction angle, by signal level, by frequency range, by coupling method, and by the quantity being amplified. Let's look at each of these one by one. The first way to classify amplifiers is by transistor configuration, based on which terminal is common to both the input and output signals. In the common-emitter or CE configuration, the amplifier provides both voltage gain and current gain and produces a 180-degree phase reversal between input and output. In the common base or CB configuration, the amplifier provides high voltage gain, but its current gain is less than unity, which makes it suitable for high frequency applications. In the common collector or CC configuration, also called an emitter follower, the amplifier provides high current gain and a voltage gain close to unity and is commonly used for impedance matching. The second classification is based on conduction angle, the duration in degrees for which the transistor conducts during the input cycle. Class A amplifiers conduct for the complete 360-degree input cycle. They offer good linearity but low efficiency. Class B amplifiers conduct for 180 degrees of the cycle. They offer higher efficiency but may produce crossover distortion. Class AB amplifiers conduct for more than 180 degrees but less than 360 degrees, balancing linearity and efficiency. Class C amplifiers conduct for less than 180 degrees. They are highly efficient but are mainly suitable for tuned radio frequency circuits. The third classification is based on signal level, the magnitude of the input and output voltage and current. Small signal amplifiers amplify low amplitude signals with minimum distortion, while large signal or power amplifiers deliver significant power to loads such as loudspeakers. The fourth classification is based on the frequency of the input signal. This gives us DC amplifiers, audio frequency amplifiers, intermediate or mid-frequency amplifiers, radio frequency amplifiers, and wideband or video amplifiers. The fifth classification is based on how amplifier stages are coupled together in a multi-stage configuration. This gives us RC coupled amplifiers, transformer coupled amplifiers, direct coupled amplifiers, and impedance or LC coupled amplifiers. The sixth and final classification is based on what quantity is being amplified, giving us voltage amplifiers, current amplifiers, and power amplifiers. That covers all 6 ways amplifiers can be classified. Now let's look at why we need mathematical models for transistors in the first place. Transistor behavior can be described using mathematical expressions, and this is useful for several reasons. It helps us calculate gains, voltage, current, and power. It helps us determine input and output impedances. It helps us select suitable component values when designing an amplifier. It allows us to simulate transistor circuits before we build them. It lets us study frequency response by adding internal capacitances at high frequencies, and it helps us predict distortion when the transistor's operation becomes nonlinear. With that motivation in mind, let's look at the BJT models used specifically for mid-frequency analysis. The mid-frequency BJT models apply over an approximate frequency range of 100 Hz to 100 kHz. There are three main mid-frequency BJT models. The first is the h-parameter model. It treats the transistor as a two-port network using four parameters: input resistance HIE, reverse voltage ratio HRE, forward current gain HFE, and output admittance HOE. This model is convenient because its parameters can be obtained directly from transistor characteristics or data sheets. The second is the hybrid pi model. It represents the transistor using the base to emitter resistance R-pi, a controlled current source gMV-pi, and an output resistance RO. It is physically meaningful, accurate, and can be readily extended to high-frequency analysis by including junction capacitances. The third is the RE model. It uses the transistor small signal emitter resistance RE, which is approximately equal to VT over IE, or about 25 millivolts over IE. It provides a simple and quick method for analyzing voltage gain and input resistance, particularly in common emitter and common base amplifiers. All three models describe the same small signal transistor behavior, but they use different parameters and equivalent circuit arrangements. Let's start with the first of these three, the h-parameter model. The h-parameter or hybrid parameter model is used for mid-range frequencies. It treats the transistor as a two-port network, which makes it convenient for calculating voltage gain, current gain, input impedance, and output impedance. It's often preferred for basic amplifier analysis because its parameters can be obtained directly from the transistor's input and output characteristic curves. For a common emitter transistor, the parameters are HIE, the input resistance, HRE, the reverse voltage feedback ratio, HFE, the forward current gain, and HOE, the output admittance. This is a useful model at mid-frequencies because these parameters can be treated as real numbers rather than complex numbers and are approximately constant. The hybrid pi model is preferred for detailed circuit design and high-frequency analysis because its elements correspond more closely to the transistor's internal physical operation. The RE model is useful for quick calculations, but it isn't generally preferred for complete BJT amplifier analysis because it's a simplified model. For mid-frequency small signal analysis, we first bias the transistor at an operating point or Q point. Small changes in voltage and current around this point are then assumed to be approximately linear. So the nonlinear transistor can be replaced by a linear model such as the h-parameter, hybrid pi, or RE model. In short, these transistor models convert a complex semiconductor device into a manageable circuit representation that we can analyze using Ohm's law and Kirchhoff's laws. A two-port network is an electrical circuit represented by two pairs of terminals or ports. A port consists of two terminals with current entering one terminal and leaving through the other. The input port is where the input voltage V1 and current I1 are applied. The output port is where the output voltage V2 and current I2 are measured. For the general h-parameter representation, V1 equals H11 times I1 plus H12 times V2, and I2 equals H21 times I1 plus H22 times V2, and I2 equals H21 times I1 plus H22 times V2. For a BJT, these become BE equals HIE times IB plus HRE times VCE, and IC equals HFE times IB plus HOE times VCE. Here, HIE represents input resistance, HRE represents reverse voltage feedback, HFE represents forward current gain, and HOE represents output admittance. We will study the h-parameter model of the BJT in more detail in the next lesson. Next, let's look at the hybrid pi model. The hybrid pi model is preferred for use in high-frequency analysis. In this model, R pi is the small signal resistance between the base and emitter given by R pi equals beta over Gm, which equals beta times Vt over Ic. The controlled current source is Gm times Vπ, giving a collector current of Ic equals Gm times Vπ. The transconductance Gm is given by Ic over Vt, and Ro is the output resistance, approximately equal to Va over Ic, where Va is the early voltage. Finally, let's look at the Re model. The Re model is a simplified model of the BJT. There are two versions, one using a voltage controlled current source and one using a current controlled voltage source. This model is useful for simplified analysis. It assumes alpha is approximately equal to 1, effectively neglecting base current effects. It neglects the output resistance Ro and therefore does not represent the early effect, and the reverse feedback from collector to base is not explicitly represented. That brings us to the end of this lesson on BJT models. We looked at how amplifiers are classified, why transistor models are needed, and the three mid-frequency BJT models, the h-parameter model, the hybrid pi model, and the Re model. In the next lesson, we'll explore the h-parameter model in more detail. Thank you.